My name is Dr. Ralph DeFranco, and I'm Professor of Medicine and Chief of the Diabetes Division at the University of Texas Health Science Center and the Audiel Murphy VA Hospital in San Antonio, Texas. I also serve as the Deputy Director of the Texas Diabetes Institute. I'd like to welcome all of you to this presentation on GLP-1 in type 2 diabetes, a primer. The objectives of this presentation are to describe the physiologic role of native GLP-1 and the impact of incretin impairment in type 2 diabetes. I'd like to review the role of native glucagon-like peptide 1, which is referred to as GLP-1 in glucose homeostasis. We know that in response to meal ingestion, the gut releases GLP-1 as well as glucose-dependent insulinotropic polypeptide, known as GIP. The release of GLP-1 stimulates insulin secretion from the beta cells in a glucose-dependent manner. What this means is that when the glucose drops back into the normal range, the GLP-1 stops augmenting insulin secretion, and this is a built-in mechanism that protects one against the development of hypoglycemia. GLP-1 also suppresses glucagon secretion from the alpha cells, and this is very important because we know that diabetics have elevated glucagon levels and their liver is supersensitive to glucagon. And the elevated glucagon levels and increased hepatic sensitivity play an important role in the excessive rate of glucose release by the liver, which primarily accounts for the increase in fasting glucose. We also know that GLP-1 slows gastric emptying, which is good particularly in newly diagnosed diabetics who have an accelerated rate of gastric emptying. By slowing gastric emptying, GLP-1 is going to decrease the rate of entry of carbohydrates into the systemic circulation. And lastly, GLP-1 has an important effect on the brain, and in particular, a certain area of the hypothalamus that inhibits satiety and gives a feeling of fullness that suppresses appetite and contributes to weight control. We also know that the incretin effect is markedly reduced in type 2 diabetics, and this is shown on this slide. This is the classic study by Professor Nock many years ago, which demonstrates the important role of incretin hormones. So what they did was take healthy, normal glucose-tolerant control subjects, and they gave them an oral glucose load, shown by the yellow squares on the top left graph. You can see that there's an initial rise in glucose, followed by a decline. And then they took these same individuals and they brought them back on a separate day, and they gave them an intravenous glucose infusion to mimic the rise in blood glucose seen following oral glucose ingestion. You can see by the diamonds in red that they did a very good job. Now, if we look in the upper right-hand panel, you can see when the glucose is ingested, the yellow squares, that the amount of insulin that is released is about threefold the amount of insulin released when the same subjects receive the glucose intravenously, the red diamonds. And this difference in insulin levels between oral and intravenous glucose refers to the incretin effect. And obviously, this incretin effect is explained by two factors: how much incretin hormones are released, and how sensitive the beta cell is to the stimulatory effect of the incretin hormones. Now, what about the incretin effect in type 2 diabetes? The classic study is shown in the bottom left panel in type 2 diabetics. And you can see the diabetics, of course, start with a higher fasting glucose. And when they are given the glucose load, there's an excessive rise in glucose above baseline. But the important thing is that when the diabetics were brought back and received glucose intravenously, they very closely mimic the blood sugar rise and decline. And when you look in the right-hand panel, if you look at the difference in the insulin response when the glucose is given orally, yellow squares, versus intravenously, red diamonds, the incretin effect is markedly reduced. The major abnormality responsible for the decreased incretin effect is thought to be related to impaired GLP-1 activity. Now, as shown on this slide, native GLP-1 stimulates insulin secretion and inhibits glucagon secretion in a glucose-dependent manner. Let me have you focus on the middle panel. You can see by the blue triangles that when native GLP-1 is administered, there is an increase in insulin secretion. And in the left-hand panel, you can see there's a decline in the blood sugar level. However, when the blood sugar starts to approach 90 milligram per deciliter, you can see that the blood sugar level starts to plateau, and it starts to plateau importantly because there's a decrease in insulin secretion. Now, in the right-hand panel is shown the plasma glucagon response to GLP-1. Initially, there's a very nice decline, but again, as the blood sugar level returns to the normal fasting level, the glucagon levels start to increase. So the increase in glucagon and the decrease in insulin protects the patient from the development of hypoglycemia. This slide shows the potent effect of native GLP-1 on the first and second phase insulin responses. On the left, we show the response to the amino acid arginine, but what I really would like you to do is to focus your attention on the right panel of this slide. In this study, Dr. Zander performed what we called a hyperglycemic clamp, in which the blood sugar level is acutely raised by a prime continuous infusion of glucose and clamped at a hyperglycemic level. Now, prior to the start of GLP-1, as shown by the blue diamonds, during the first 10 minutes, you can see that there's virtually no first phase insulin response. And then over the next 50 minutes, there's a very blunted second phase insulin response. At 50 minutes, arginine is administered, and you can see a nice kick out of insulin. So the beta cell responds well to amino acids in diabetics, but responds poorly to glucose. So one of the characteristic defects, and it's shown very nicely in this slide, is the beta cell blindness to glucose in type 2 diabetes. Dr. Zander then took these individuals who had type 2 diabetes and admitted them to the Clinical Research Center and continuously infused native GLP-1 through an infusion pump. And he had to continuously infuse the GLP-1 because the half-life of GLP-1 is very short, in the form of minutes. And then after 1 week, he repeated the hyperglycemic clamp, and that is shown by the solid orange squares. You can see that within 1 week, there is a restoration of first phase insulin secretion and a marked increase in second phase insulin secretion. The effect of arginine is unaltered because there's no abnormality in arginine-stimulated insulin secretion to start with in the diabetics. And then the patients continued to receive the intravenous GLP-1 infusion over the subsequent 6 weeks. And you can see by the yellow triangles that the improvement in first and second phase insulin secretion persists. So this study clearly showed the effect of native GLP-1 to reverse the characteristic defects in insulin secretion that are present in type 2 diabetics. So in the study by Zander, when patients received intravenous GLP-1 infusion and were in the Clinical Research Center for 6 weeks, taking in a fixed dietary intake, you can see, as shown in this slide, that there was a weight loss of about 4 pounds, whereas in the group receiving saline therapy, the weight changed very little, by only 1 pound. Now remember, these people in the Clinical Research Center are taking in a fixed dietary intake, so the ability to cut down on the energy consumption was quite modest. In real life, patients are able to control their food intake, which may impact weight change. This slide demonstrates the severe insulin resistance to GLP-1 present in type 2 diabetic patients. The left-hand panel shows the plasma insulin response on the y-axis as a function of time when GLP-1 is infused at a rate of 0.5 picomoles per kilogram of body weight per minute to raise the plasma GLP-1 level to 46 picomoles per liter. In the bottom line, you can see that in the type 2 diabetics, the same GLP-1 infusion that raised plasma GLP-1 similarly to 41 picomoles per liter virtually had no effect to augment insulin secretion. These data suggest impairment of GLP-1 activity at the level of the beta cell. Now, in the right-hand panel, diabetic patients received the GLP-1 infusion that was double that in the study on the left. And this raised the GLP-1 levels to 126 picomoles per liter, 3 times what is shown on the left-hand panel. And you can see now that when you cause the pharmacologic increase in GLP-1, you can get an increase in insulin secretion that is virtually identical to what we see in the normal healthy controls. So in effect, a pharmacologic increase in GLP-1 levels with native GLP-1 overcomes the resistance at the level of the beta cell and leads to a marked increase in insulin secretion. As we've reviewed, GLP-1 is an incretin hormone important in many physiologic processes, in particular in augmenting insulin secretion and in inhibiting glucagon secretion. And these two effects play a critical role in maintaining normal glucose homeostasis. We've seen how the impaired incretin effect is a key component of type 2 diabetes, but that insulin response is improved and glucagon suppression is enhanced by pharmacologic levels of GLP-1, resulting in improved glucose levels. In addition, GLP-1 has been shown to reduce body weight.